Here are our solutions to homework set number 5 for ECE 463-663 Modern Control. The first problem is to write a MATLAB subroutine pole placement that gives a systems A and B matrix. Again, I'm assuming the system's in state space form, so x dot equals AX plus BU. Find the feedback gain Kx so that if U is minus Kx times x, the closed loop system becomes x dot is A minus BKX times x. Find Kx to place the poles of the closed loop system. And the approach is to use Gura. That is, I define a similarity transform that takes you to controller canonical form. And your transformation matrix is made up of 3 terms. The first one, T1, is the controllability matrix, not surprisingly. T2 is the open loop system's characteristic polynomial, and T3 is a flip matrix. That takes you to controller canonical form. In controller form, the feedback gains are really easy. It's just the difference between the desired characteristic polynomial and the actual characteristic polynomial. The feedback gains in x then is similarity transform, switch from z to x. And as a check, if I take a random A and B matrix, place the poles at minus 1, 2, 3, and 4, it finds the feedback gains, and sure enough, the poles of the closed loop system are at minus 1, 2, 3, 4. So that's problem 1. The rest of the homework, in fact the rest of the homework for the rest of the semester, will be using that routine. Problem 2 says, here's the heat equation. It's a 5-stage RC filter. Find the feedback gains that place the dominant pole at minus 2 and the other poles out of harm's way. So really what I want is I want this step response. I want to have no overshoot, a settling time of 2 seconds, and a DC gain of 1. Find the feedback gains that give you that response. So using Gura, I input the A matrix, B matrix, find the feedback gains, and you get something. As a check, the poles of the closed loop system are sure enough where I put them, minus 2, 8, 9, 10, 11. To find Kr, make the DC gain 1. So here's the DC gain if Kr equals 1 is wrong. Pick Kr to make the DC gain 1. So there's Kr, 5.06. As a check, I'll form the closed loop system, plot the step response. Here's the closed loop A matrix, B matrix. Here's the output Y, C and D, and here's the output U. U is minus Kx times x plus Kr times R. Find the step response and then plot it. And here the trick is I plotted the second column times 1/10. So this is Y and this is U over 10. The reason I did that is U is swamping the output. But anyway, this is kind of what you expect. Here's the constant U to hold the output. Initially, I slam U high. That gives you a quicker response. So that was problem 2. Problem 3 says, well, the input was fairly large. Okay, on to problem 3. Problem 3 looks at the same problem as before. I want the same step response. I want to have no overshoot, a 2-second settling time, DC gain of 1. So that's where the dominant pole belongs. The other poles, however, I don't really care where they go. So maybe a better spot is to leave them alone. This is where the open loop poles are. Let's make the closed loop poles exactly the same. Except the dominant pole, let's move that to minus 2. Conceptually, if I do less, it takes less control effort. I should get smaller gains. Previously, Kx was about 2.9 for the biggest gain. Now it's 0.9. Smaller gains means less inputs. That's good. Find Kr. Yeah, it's about the same. Take the step response to the closed loop system. Now here's what it's looked like. Previously, the input did this and went down. I now have a much better behaved input. So that's one of the strengths, also one of the weaknesses of pole placement. You can get better responses. The poles that aren't dominant do have an effect. They affect the input. If I try to move the poles too far, that takes energy, that takes control effort. That shows up in large inputs. So some spots are better than others. The challenge is, where do I want to put the other poles that aren't dominant? And that's one of the problems with pole placement. The last problem, according to pole placement, I can put the poles anywhere. So let's try it. Let's try to force a heat equation to oscillate. Again, heat equations don't like to oscillate, but in theory I can do anything. So let's try it. Let's take the open loop poles and move them. I'm going to leave these 3 poles alone, take the 2 dominant poles, and then make it oscillate. It's going to have a 2-second settling time and 10% overshoot, so I should get this kind of response. And that's 10%. So the settling time tells you the real part, the angle tells you the overshoot. In the second order damping curves, 10% overshoot corresponds to zeta is 0.591. You can use the table for the second order approximations if you want. That tells you the angle. Once I have the angle, I know the real part. Using some trig, I can find the complex part. Net result is that's where I want to put the dominant poles. So to do that, same procedure as before. Pole placement can do anything. Put the poles anywhere you want. If this is where I want to put the poles, here's my feedback gains. And it doesn't really care. Find KR. KR is bigger than before. It was 5, now it's 8. That's kind of telling me that it takes more control effort to get this response, which isn't surprising because I'm trying to make a heat equation oscillate. Here's my output, this is Y. Here's my input, U over 10. Same trick as before, I'm just trying to keep U from swamping the output when I plot it. And you can see I have a much larger control effort. I need that to get the dang thing to oscillate. Then I actually kind of undershoot a little bit. Try to get it to come back down. The net result is it works. And that's the beauty of pole placement. Any response you want, you can do. Some responses might take a lot of energy, but as McDonnell Douglas says, in thrust we trust. If you have enough power, I can do anything. So that's homework set number 5 for ECE 463 Modern Control.